Welcome back. Now we're going to look at the section 3.4.2, which is the secondary method for solving non-homogeneous linear equations. And this is the method you would use after you check to see if the undetermined coefficients method doesn't work. So what are some of the conditions where it doesn't work? Well, one would be if you have coefficients that are not constant, and two, if the function on the right-hand side doesn't have a simple or finite derivative form, pattern of its derivatives. So we'll first lay out the procedure, look at an example with a function that does work just fine with the undetermined coefficients, and then we'll work through the process of understanding exactly how the method works. And in class, we'll go through some more examples on what problems you would need this method for. Okay, so the method of variation in parameters starts off with your check. That is, you need a linear equation where your f of t can be integrated. With the method of undetermined coefficients, we needed to have a function on the right-hand side which had a finite pattern in its derivatives. In this case, we're looking on the opposite end. Do we have a function we can integrate? There are a couple of functions that we get stuck integrating, and so this can lead to some issues. But even when we can't integrate out these things, we'll find that there are ways to get around it later on. So it's a very general case. We can work with most functions. It's just telling us that the integration can get complicated. If it gets too complicated, then this method is not as helpful. First step, just like the method of undetermined coefficients, is to find x of h. But in this case, we are able to find the homogeneous solution even in some cases where the coefficients are not constant. So we'll see an example of that later. After we find x of h, we want to write it in the form c1 x1 of t plus c2 x2 of t. And in the second step, we form our particular solution by varying the parameters. In this case, we vary the constants. This c1 becomes some v1 function of t times x1. The c2 becomes some v2 of t times x2. Now these v1 and v2s are functions of t, but they are helper functions, just like the integrating factor in the integrating factor method in chapter 2 was a helper function. We're going to solve for v1 and v2 in a similar way. We only need one example v1 and one example v2. Here we vary the parameters. Now, I'm going to write down what the v1 and v2 solutions are, and then a little bit later I'll derive how we get there. But using the assumption that we only need one possible helper function, we can make a condition on v1 and v2 to be able to solve it as v1, the integral of the 0 and f of t in the first column of our determinant system, and x2 and x2 prime, divided by the Wronskian of x1 and x2. Now this top piece looks very similar to the Wronskian. The Wronskian would be x1, x1 prime, x2, x2 prime. The only difference is that we've copied over that first column some pieces that refer to the right-hand side. In fact, this function is the function on the right-hand side, the piece on the right-hand side. So this ratio of determinants is from Cramer's rule. And we refer to this top determinant as W1, and we refer to the Wronskian on the bottom as W. And in the same way, V2 is the integral of W2 over W1, where W2 is your x1, x1 prime from your homogeneous solution. And then 0 f of t, taking that right-hand side piece and pasting it over the second column, divided by the Wronskian of x1 and x2. And we can refer to these two pieces as W on the bottom, and on the top this time it's W2, or the determinant of the matrix modified by pasting the resultant piece 0 f of t onto the second column. Okay, so that's the mechanics of what we're doing with the variation of parameters method. So that immediately gives us the pieces we scale the x1 by and we scale x2 by. Notice that these will be functions. V2 is a function of t, V1 is a function of t, V2 is a function of t, and it scales x1 and x2 in a nonlinear way to form the particular solution that gives you the right-hand side function, that forcing function. So this is a very different approach that is more reminiscent of the integrating factor method from chapter 2. Whereas the energy coefficients method looks at some of the pattern of the derivatives, here we're actually looking at the homogeneous solution and combining them in a non-linear way to get our solution. After we have that, it's just downhill from here. We use the same form for the general solution. We just coast down. X is equal to x of h plus xp. Just add those two pieces together. And finally, we can apply initial conditions, if we have any. So that is the procedure of the method. Let me go through an example to see how this, a quick example to see how this procedure is used. X double prime minus x equals e to the negative t. Okay, so first thing we do is find the homogeneous solution. So we write down r squared minus 1 equals 0. We get r squared equals 1, r equals plus or minus 1. Okay, so we know that our roots are real, and we get x of h equals the span of e to the negative t, e to the positive t equals c1 e to the negative t plus c2 e to the positive t. And then we look at forming xp from this piece. Okay, so that's how we're going to put the pieces together. We need to calculate the Wronskian of this function and the two modified pieces to take the ratio. So first, the Wronskian, e of negative t and e to the t. Now, Notice that we need that Wronskian to be non-zero for this to work, and that means that the pieces we are spanning in our homogeneous solution must be linearly independent. But we've already been over that, so they are. Because we have exponentials with different exponents on the top, distinct exponents. Multiplying down, we get a 1. Subtract, multiplying back up, we get another 1. That's 2. Okay, so that's our Wronskian. That's what we're going to be dividing by each time. V1 is the integral of our modified Wronskian, so replacing this first row with 0 and f of t. In this case, it's e to the negative t. And e to the t stays the same. On the bottom, we just divide by the Wronskian, which we calculated to be 2. And then we compute. Now, we can't integrate yet. We have to take the determinant here. So we multiply down. We get a 0. And we subtract, multiply up. That's a 0 minus 1. Okay, so that's the ratio of the two Wronskians, negative 1/2. And then we integrate that. We get a negative t over 2. Now that has a plus c, but because this is a helper function, we only need one of them. We're going to ignore that plus c. Because we choose the negative t over 2. We choose the simplest version, just like the integrating factor. Then on our V2, we get the second modified Wronskian. So we have the first column the same. Second column this time is 0 and f of t, which is e to the negative t. Divide by 2 again. And multiply down, we get a e to the negative 2t. And back up, we get minus 0. Okay, a little bit more interesting on the integration. We get a e to the negative 2t divided by negative 4 plus c. Again, we choose the simplest version of this, so we ignore plus c there. And let's combine our terms together. xp is equal to v1 negative t over 2 times e to the negative t plus v2, that'd be a minus, negative 4, minus e to the negative 2t over 4 e to the t. And then we can simplify that a little bit. Negative t over 2 e to the negative t minus 1/4 e to the negative t. Now, this is interesting. This is a particular solution. But if you look at the homogeneous solution, we already have a constant multiple of e to the negative t. So that means that we don't need this piece. This is already part of x of h. And in 3.1, you proved that the difference between any two particular solutions is simply a functional piece of the homogeneous solution. So we can simplify, we can cut to the chase by pulling out and kind of ignoring every piece of the particular solution that is already in the homogeneous solution. And so I will choose my xp to be just the piece that is linearly independent of my homogeneous solution. And I can write that all together. So x equals xh plus xp. C1 e to the negative t, which again pulls in this extra minus 1/4, right? Pulls into that constant, plus C2 e to the t minus t over 2 e to the negative t. Okay, so there's a quick example. Notice that this method can take a little bit of time with the integration, but you're not having to expand lots of different pieces and plug them in. We are instead just using this determinant combination to form a ratio of functions which we can then integrate out. So sometimes it's a little bit, it seems a little bit more intuitive and it's a little bit more straightforward and less guess and checky in a sense. So I really like this method. It can be long in certain cases. So just, think about the combinations of functions which don't iterate very well. Think about the functions that maybe perhaps cause problems when you differentiate them and pull them apart. We'll look at some examples to see how it compares in class. Okay, so now we're going to take a break and look at the derivation of how this ratio of Wronskians occurs and why we choose 0 and f of t to be our right-hand side. Well, how do we get two pieces? So that's coming right up.